All right, yo, what's up? Break from studying. I hope you guys been well. Sorry I'm a day late, but yeah, I want to talk about biconditionals today. Um, and the agenda will be to create a truth table for a biconditional, and then we're going to analyze the truth table to better understand some of its properties. And these are some of the takeaways that I have, and maybe as I talk about this, it'll trigger some other important things that I forgot to include here. Okay, so what is a biconditional? Biconditional is a special type of statement. Oh, sorry if I'm whispering like this, like bootleg ASMR. My roommate is on the other side, and I'm not sure if you can hear me. So, yeah. All right. So, what was I saying? Yeah. So, biconditional is a special type of statement using this logical connective, and it's basically it looks like two arrows, one facing the left, one facing the right. And what you put here on the left is a statement. So we typically use P to represent a statement, and then Q for the other statement. And sometimes they say that this double arrow means IFF, and that means if and only if. So when you say this is like saying P if and only if Q. And there are other ways of saying biconditional, but here's another common one, logically equivalent. So sometimes when you see this, people will say that P is logically equivalent to Q. Okay, so P is logically equivalent to Q. And we'll see why, okay, by looking at the truth table. Um, in high school, I think they just straight up, sometimes when they give this the statement, P if and only if Q, uh, they won't really talk about this piece. Okay. But fundamentally, or more fundamentally, this biconditional P if only if Q is technically an and statement of two implications. The first implication is the OG implication, the original implication. So P implies Q and its converse. So Q implies P. So technically, P, this P if only if Q, this is this means logically equivalent. Okay. Um, it's this. P implies Q, and let me put that in parentheses just to emphasize that that's one statement. And it's a logical connective. The converse is Q implies P. Okay, so that being said, let's generate the truth table for this. Okay, so if you haven't already, please take a look at the other videos on logic quiz and that other logic video. I talk about how to create one. So I'm going to assume that you know that. Okay, so here, let me start with a statement P. And this is not thick enough. Yeah, so start with a statement P and another statement Q. There are four different possibilities. I'm just going to write this TFTF and then TTFF. Once again, check out the other video if you're wondering where these came from. Okay, and then I want to build this. So let me I'll use a different color. So P implies Q. Okay. So from the other video with implications, we said that this is going to be true in every case except when the conclusion is false and the hypothesis is true. So I'm just going to put T. This is false, and this is T, and this is T. Similarly, we can create the truth table for the converse. So Q implies P. And I'm just joining multiple state uh, truth columns into like one table, right? But you could do these separately, but it's the same thing. Okay, so Q implies P. Um, Same way, you could use this the first two columns to do this, but instead of looking left to right, look right to left. Okay, so it's still an implication, but this time the conclusion is your P now. So then that means that it's going to be true in every single situation except when the hypothesis, which is Q now, is true and the conclusion, which is P now, is false. So it's this. So it's going to be P, P, F, T. Okay. Okay, great. And now to create this is what we want, right? We want to create this P if and only if Q. But if I'm saying that this is actually a conjunction, I could put this entire thing here, right? So P implies Q and Q implies P. And don't look too into this. Just think this is just one big AND statement, right? So here to find the truth values for these, you just look at this part, this column, and this column. Okay. So, and then I'm assuming that you also know how the and statement works. Okay. But here, uh, they're both true. So this is true. Um, one's false. So this has got to be false. Same thing here. This is false. And these are both true. So this is true. So in conclusion, the truth table for the biconditional, this thing, which is the same as this, is just this column. Okay. So if we break this down, we simplifying this table, I'm not going to do it. I'm just going to just look at column 1, 2, and last column here. Okay. Now let's analyze this. It's saying that this biconditional, you know what? Let me just write P if only a Q here. Right. Right. So it's saying that P if and only if Q is true in situations 1 and 4. Right. So go back to the original P and Q. It's saying that P if and only if Q is true when both P and Q are true. Or it's also true, and it's also true if uh, both P and Q are false. But in cases 2 and 3, where P and Q have different truth values, this is false. Okay? So this will help you. Okay, this will help you remember. Okay, especially for this one. Okay, so when people say, "Oh, uh, P is logically equivalent to Q," the way that you would use this typically, especially in like higher math, when you have proofs and stuff, very useful. If I know, if I'm given a biconditional, um, and I know one of these pieces, P, if I know this is false, right? Then I know the other one has to be false. Okay. If I'm given a biconditional that's true, okay. So sometimes you like for example, I don't have this at the top of my head, but like in a class called linear algebra, they have something called the equivalence theorem, and then they say, oh, all of these statements are logically equivalent. So they give you like 7 statements, and if you know that one of them is true, then you get the other 6 for free. And vice versa too. Like if you know that one of them is false, then all of them have to be false, right? Because of this. All right. I hope that made sense. So once again, this video is probably overkill for high school geometry. Probably more useful for like intro to proofs course, but I think you can learn this yeah, like in high school too. And it's just really, really good if you just want to get a good uh foundation for mathematics and stuff. So yeah. All right, so my break is done. I'm gonna go for a run and peace out.